Invisible dark matter makes up most of the universe, but we can only detect it from its gravitational effects. Galaxies in our universe seem to be achieving an impossible feat. They are rotating with such speed that the gravity generated by their observable matter could not possibly hold them together. They should have torn themselves apart long ago. The same is true of galaxies in clusters, which leads scientists to believe that something we cannot see is at work. They think something we have yet to detect directly is giving these galaxies extra mass, generating the extra gravity they need to stay intact. This strange and unknown matter was called dark matter, since it is not visible. Dark matter. Unlike normal matter, dark matter does not interact with the electromagnetic force. This means it does not absorb, reflect or emit light, making it extremely hard to spot. Dark matter seems to outweigh visible matter roughly 6 to 1, making up about 27% of the universe. Here's a sobering fact: the matter we know and that makes up all stars and galaxies only accounts for 5% of the content of the universe. But what is dark matter? One idea is that it could contain supersymmetric particles, hypothesized particles that are partners to those already known in the Standard Model. Experiments at the Large Hadron Collider or LHC may provide more direct clues about dark matter. Many theories say the dark matter particles would be light enough to be produced at the LHC. If they were created at the LHC, they would escape through the detectors unnoticed. However, they would carry away energy and momentum, so physicists could infer their existence from the amount of energy and momentum missing after a collision. Dark matter candidates arise frequently in theories that suggest physics beyond the Standard Model, such as supersymmetry and extra dimensions. One theory suggests the existence of a hidden valley, a parallel world made of dark matter having very little in common with matter we know. If one of these theories proved to be true, it could help scientists gain a better understanding of the composition of our universe and, in particular, how galaxies hold together. Dark energy. Dark energy makes up approximately 68% of the universe and appears to be associated with the vacuum in space. It is distributed evenly throughout the universe, not only in space but also in time. In other words, its effect is not diluted as the universe expands. The even distribution means that dark energy does not have any local gravitational effects, but rather a global effect on the universe as a whole. This leads to a repulsive force, which tends to accelerate the expansion of the universe. The rate of expansion and its acceleration can be measured by observations based on the Hubble law. These measurements, together with other scientific data, have confirmed the existence of dark energy and provide an estimate of just how much of this mysterious substance exists. The Standard Model. The Standard Model explains how the basic building blocks of matter interact, governed by 4 fundamental forces. Everything in the universe is found to be made from a few basic building blocks called fundamental particles, governed by 4 fundamental forces. Our best understanding of how these particles and 3 of the forces are related to each other is encapsulated in the Standard Model of particle physics. Developed in the early 1970s, it has successfully explained almost all experimental results and precisely predicted a wide variety of phenomena. Over time and through many experiments, the Standard Model has become established as a well-tested physics theory. Matter particles. All matter around us is made of elementary particles, the building blocks of matter. These particles occur in 2 basic types called quarks and leptons. Each group consists of 6 particles, which are related in pairs, or generations. The lightest and most stable particles make up the first generation, whereas the heavier and less stable particles belong to the second and third generations. All stable matter in the universe is made from particles that belong to the first generation. Any heavier particles quickly decay to more stable ones. The 6 quarks are paired in 3 generations. The up quark and the down quark form the first generation, followed by the charm quark and strange quark, then the top quark and bottom, or beauty quark. Quarks also come in 3 different colors, and only mix in such ways as to form colorless objects. The 6 leptons are similarly arranged in 3 generations, the electron and the electron neutrino, the muon and the muon neutrino, and the tau and the tau neutrino. The electron, the muon and the tau all have an electric charge and a sizable mass, whereas the neutrinos are electrically neutral and have very little mass. Forces and carrier particles. There are four fundamental forces at work in the universe: the strong force, the weak force, the electromagnetic force, and the gravitational force. They work over different ranges and have different strengths. Gravity is the weakest, but it has an infinite range. The electromagnetic force also has infinite range, but it is many times stronger than gravity. The weak and strong forces are effective only over a very short range and dominate only at the level of subatomic particles. Despite its name, the weak force is much stronger than gravity, but it is indeed the weakest of the other three. The strong force, as the name suggests, is the strongest of all four fundamental interactions. Three of the fundamental forces result from the exchange of force carrier particles, which belong to a broader group called bosons. Particles of matter transfer discrete amounts of energy by exchanging bosons with each other. Each fundamental force has its own corresponding boson. The strong force is carried by the gluon, the electromagnetic force is carried by the photon, and the W and Z bosons are responsible for the weak force. Although not yet found, the graviton should be the corresponding force-carrying particle of gravity. The Standard Model includes the electromagnetic, strong and weak forces and all their carrier particles, and explains well how these forces act on all of the matter particles. However, the most familiar force in our everyday lives, gravity, is not part of the Standard Model, as fitting gravity comfortably into this framework has proved to be a difficult challenge. The quantum theory used to describe the micro world, and the general theory of relativity used to describe the macro world, are difficult to fit into a single framework. No one has managed to make the two mathematically compatible in the context of the Standard Model. But luckily for particle physics, when it comes to the minuscule scale of particles, the effect of gravity is so weak as to be negligible. Only when matter is in bulk, at the scale of the human body or of the planets for example, does the effect of gravity dominate. So the Standard Model still works well despite its reluctant exclusion of one of the fundamental forces.